Okay, so hello, welcome to the fourth lecture video on model-free control. So where are we right now? So we began with a formal definition of Markov decision processes where we actually define what an optimal controller should look like. We then get to know dynamic programming techniques, maybe policy iteration and value iteration, in order to estimate such an optimal controller. In the last lecture, we actually made everything a little more real-worldy in case that we say, what if in practice we do not have a model? So we actually cannot just calculate everything because we do not know the probability transition matrix and the dynamics of our environment. In the last lecture, we actually saw methods, namely Monte Carlo, policy evaluation and TD learning, which actually let us both estimate a value function given a certain policy pi. In this video, however, we will now actually deal with a control problem. So in the end, we want to find a policy pi that actually maximizes the expected return that we can squeeze out of our MDP. And this is what we will do in this lecture. So let's just, in the beginning, let us define a few things first. Let us define the model-free control problem. So as also in the lecture last week, we are actually given experience samples as maybe depending on or being S, A, R, and S prime. So we have state action pairs. We get a reward actually executing this action in the state, and we get the information about the successor state. And now the basic idea behind the model-free control problem is actually to learn a close to optimal policy pi that lets us optimally behave in the environment. So from my impression, I would say this is actually the point where we actually aimed at. Finally, we are at a point where we have everything that we need to understand to actually put an agent in an unknown environment and let it learn how to act maximally efficient. Okay, so how would we actually deal with it? How would we actually do this? So a very simple idea would just be to say, okay, if we have calculated the value function through means of TD learning or some other policy evaluation or policy estimation technique for a given policy pi, we can do this with Monte Carlo or TD learning as we did it in the last week. We can use it to derive a better policy pi prime through greedy policy improvement over our value function. This is actually what we introduced also in policy iteration in the second lecture where we introduced dynamic programming. And maybe you also remember our basic framework, which was generalized policy iteration, where we have interleaving steps of starting with an initial estimate of our value function and initial policy, which might be a random policy and also a random value function initialization. And what we first do is we actually estimate the value function given a certain policy pi. And if we do this, we update our policy greedy and just do a greedy policy improvement over our value function. Last week, so if we do this with the obviously in the model-free setting, we could, for instance, use Monte Carlo policy evaluation as we introduced it last week. However, there is actually a problem with the greedy policy improvement. And before I go to the next slide, maybe think about what could the problem be with the greedy policy improvement step in this scenario. All right, so maybe just go a step back and actually look at what we're actually doing if we say we do a greedy policy improvement over our value function. And this is actually what the greedy policy improvement does and how we defined it in the second lecture. So when we estimated the new value function or the value function upon a policy pi, what we simply do is we look at each of the steps, at each of the states we have in our MDP, and we just say, okay, the action that our policy should select in a certain state S should be the action that actually maximizes the one-step return, which basically means is we want to take the action that maximizes the sum of the reward that I will get taking this action, so the immediate reward, plus the discounted weighted sum of the successor states, actually of the values of the successor states. And yeah, so actually in a model-free reinforcement learning setting, this is actually quite problematic. Can you think about why this is problematic? Okay, so the first problem is this requires a model. So actually, in order to do the policy, the greedy policy improvement step, we actually need to know the probability transition matrix P. And this is quite problematic because actually this is something that we do neither have explicitly, nor we implicitly estimate it with the policy evaluation techniques that we saw last week. However, you might have seen that at some point we also introduced the state action value function Q, and I always told to you that let's ignore Q so far because we want to get the concepts right, and you should really focus on the state value function to actually get the concept. But however, all the policy evaluation techniques and also policy iteration and value iteration work with the Q function as well. And now what's actually the difference between the state value function and the state action value function if we look a little more closely to it? So the first thing that really now in the problematic scenario that we are currently in is that the greedy policy improvement, if we do this over the Q function, this actually is a model-free operation. So actually we define, or actually what we want to do is we have a Q value per action for a single state. And the policy improvement step over the Q function would simply be to take the argmax operator over Q at a given state S, which is basically a model-free operation. But actually, how is the state action value function Q defined also in relation to the state value function? In principle, the general relation between V and Q is that the state value of a state S under pi is actually the same as the state action value of a state S at the point where the argmax operation, so actually for the action that we would select under our given policy pi. So if we break this down, we can also say, let's define the state action value function for Q, the state action value function Q for a given policy pi, which is nothing else than the expected discounted return, the sum of rewards that we can expect starting in a state S, as we also did it in the value function, but already having selected the action that we would take starting in this state. So simply and really like similar to what we did the value function. So the value function we said, okay, it's the expected return, the discounted expected return that we can get if we start in a state S. And the Q function is simply an addition and says it is the expected discounted rewards of starting in state S, but also having selected state action A to take. If we break this down, if you maybe remember, I also had it a little like very shortly in the value iteration slides. This is actually if you would do value iteration for Q values instead. And what you see here is this was the converged grid world example in the second lecture of value iteration, where we actually used value iteration to estimate the state value function. And if you see here is like the state value actually of this state is 0.85, the state value of this state is 0.64. And what you see here is the Q function. And the Q function is actually, you have for each state number of available actions Q values. And those Q values implicitly encode the one step to the next successor state. And if you see here is like the maximal Q value in here is actually 0.85, meaning that this is the state value if you are in state S and you already have selected action right to take from this state onwards, which is actually the same as in here. This is actually the value if you are in the state, what can you expect to go? So what's the actually maximum return that you can actually expect if you follow this policy, which is in this case also the optimal policy. So you will see that the maximum Q value for each cell is actually the value of each state in the state value function. We can also define the Bellman equation. So actually, if you remember, we used this principle of the Bellman equation, which is actually the idea of decomposing the value function so that we can actually run our algorithms that we already introduced onto this. And you can do this exactly the same as you did this in the state value function. So it is like really simple. So the state action value function under a given policy pi is nothing else than the first step immediate reward that you would get because you actually already selected the action A under a given state S, plus the discounted state action values of the weighted by the probability transitions of all the successor Q values that you can see. For each of them, always under your policy pi. So this is actually the first step, and this is also the subsequent step. So this is actually the Bellman expectation equation for the state action value function Q. But we're also interested in the Bellman optimality equation for Q, which is very similar as you already saw it for the state value function. So for the optimal state action value function Q, this is nothing else than the immediate reward that you would get taking action A, plus the probability transition times the maximum Q value of the successor state that you can get. So this is actually, as we also have introduced it in the dynamic programming lecture, this is actually what should be satisfied by all the states and all the Q values in your tables. And if this is satisfied, you have converged to the optimal policy. And as in the state value function, this involves a nonlinear operation here, meaning that we cannot simply span up a system of linear equations that we could solve through matrix inversion. So we need iterative methods such as value iteration or policy iteration. Another example that shows how actually the state value function and the state action value function are related. So if you maybe remember the example that we want to estimate the state value of certain routes going from your home to your workplace. And what we did in the second lecture, we actually started from the back in this case, and we assigned the state value through like no discount in this case. What is the reward that we can actually expect out of this state? And the reward was the inverse of the cost actually going to the route. So the faster you can get over an edge or over a certain road segment, the higher is your reward in this case. So in this case we said, okay, it's giving me 4. In this case there is no decision involved, so the state value is in this case 4, in this case 1. And starting from here, starting from this, they actually have 2 options, either going over this, taking an immediate reward of 3, and then having a state value that I can expect of 4, and over the right route or over the lower route, in this case, I can expect an immediate reward of 5 and a state value of 1. Which meaning that starting in this case, if I'm like behaving optimally, what I can expect is either getting the 7 over the top route or the 6 over the bottom route. Basically meaning that if I'm acting optimally, I can expect 7. And you can like forward this also to here, because if I get 10 for the immediate reward for this transition and getting 7 in here, this is more than getting an immediate reward of 1 and expecting 11 starting from here. So this was actually the state value. And now the Q value is simply like capturing the one-step transition. It somehow implements something like a one-step look ahead. So in this case, what you would say is, in this state in here, if I'm in state S2 and I would actually choose action left, what I can expect from there is a reward of 7, which is basically 3 plus the value of the next state, or actually the maximum Q value of the next state, which you will see next. And if I'm in state S2, so in here, and I would actually take the right action to go the lower transition, I can actually expect 5 plus 1, which is the 6. And instead of encoding the 7 in here, I would encode like a Q value within this state that encodes the expected return I can get given this action. And if I do this for the next state in here, we can just do exactly the same. For the maximum Q value, we would say being in the state and actually taking step left would give me the immediate return of 10 plus the maximum of the Q values of the successor state without discount anything. So it would be 10 plus 7 is 17. And for the lower example, it would be just 1 plus 11 makes it 12. And of course, the state value is actually the maximum over the is actually the one of the Q value of that maximizes the Q value, which is in this case also 17. Okay, and how would you do the greedy policy improvement, or what would your policy actually do? You would just always use the Q value that maximizes your expected return, which in this case would be just to always take the max. And if you just take the max, you implicitly have also your optimal policy. Okay. So this is actually the same slide that we had two lectures ago. Instead of doing the greedy policy improvement over V, which was like also an argmax operation, but which involved the one-step probability transition matrix in here, what we do is by estimating or by sampling the environment, we implicitly capture such probability transitions and we directly encode this information into a Q value at the cost of estimating number of action times more values than we did with state value estimation function. Okay, having cleared this up, so actually taking the Q function over the V function, we can return to our initial idea, which was basically to say, if we have calculated a value function for a given policy pi using some method, we can use this value function to actually derive a better policy. And what we just do is we plug in the Q function instead of the state value function V, and we just use, for instance, for our policy evaluation step, we estimate the Q function through maybe Monte Carlo policy evaluation. This works like straight away, as we did it in the value function as well. And then we just do the greedy policy improvement step over Q. However, there's still one problem remaining with this. So we had one problem with the policy improvement at this point because it involved like the transition probabilities and the dynamics of the environment, but there's still another problem that we have to deal with. Maybe just take a moment and think about what this additional problem could be. Okay, so if you remember, maybe there was a short sentence that we had 2 lectures ago where we said, how can we actually be sure that we estimated the value function correctly? And the argumentation was that we estimate the value function correctly because we actually follow our policy pi and we will eventually visit all the states that will be visited by our policy pi. However, if we actually search for a control policy that actually lets us estimate a value function, there is a problem, because if we always act greedy with respect to our knowledge, we might leave a little bit of the state area unexplored. So actually the problem is with the greedy policy improvement step still again. And I have a funny video because I actually think funny videos are always a good thing to remember. And the question is, the basic motivation is, how can your policy or how can your agent come up with a nice idea without actually trying something new? And this is actually also the case. If you have a policy and your policy is greedy, and you will always behave with respect and you will always try to maximize with respect to your current knowledge, you might not find better solutions in your MDP. There's also a well-known example from here. Maybe I think this is also very like intuitive. It's the thing like if you're just assume that both of them, like the one has the policy of the first person is to dig at this hole, the policy of the other person is to dig at that hole, and the value function is just the rewards that we have gotten so far. And what you see here is you have an agent or a policy that actually uses to dig in this hole, and one agent that uses the policy to dig in that hole, and you get a reward in this. And at some point you dig in here, and obviously at this point you see actually more reward if you actually dig in that hole. So you might be very like actually you want to if you want to actually maximize reward based on what you have seen so far, you would just switch holes and dig in here. However, if you are not willing to explore your environment farther and to learn more about your environment, you just get lost and you will dig here forever and you will never find the really big diamond that you would have gotten in here. So basic principle behind exploration and exploitation. Exploration deals with the trade-off of immediate reward over the exploration, and exploration means something like finding out more about your environment, of your dynamics of the environment, and also about your state action value function in your environment and how it looks like. And exploitation, in turn, exploits the known information that you already received from your environment. We will have a distinct lecture on exploration strategies later in the lecture, where we actually deal a lot with this problem again. Maybe be patient if you're more interested into there. We will have an own lecture on this. You can also come up with more examples like everyday examples. Maybe you're not digging for diamonds every day, but you see such situations a lot. Also, we as humans are faced with such situations a lot. Maybe like if you want to go to the restaurant, or if you want some lunch and you go to Liverando or something, and there's also always the case: do I go and select the restaurant that I know provides good food, or do you want to try something new? The same with online advertisements. So the question is, for some of your customers, advertisements that are actually well fitting to them. However, you need to find out more about your environment, which, if you're the advertiser, which means that you have to try new advertisements to actually see if certain persons are actually interested in those advertisements as well. The same, a very similar example to this is something maybe oil drilling, where you actually need to find oil in the sea or something like this. Maybe also a nice example, maybe also with putting in a little values with this. This could be something like that you will be faced with in the near future. Just imagine that the following situation: you're in an application interview, and the boss that you apply a job for says to you, okay, there are two doors in front of you. Behind one door is a tenure position, and behind the other door you need to flip burgers at McDonald's. You might want to not apply for a job with a boss like this, but just as a running example, we can use it. And imagine that there is some noisy random process also assigned to your reward function. So actually we define the reward function, and the reward function is actually defined as a distribution over states. So you might have some variance in the rewards that you get. And now imagine that at one time step you just open the left door and you get a 0 reward. Maybe like you open the door and you see McDonald's. This was just not by luck. So actually, if you would have opened it again, it would return something else. However, based on this knowledge, in the next step, you would open the right door, and in the right door, you maybe get a reward of +1. And now, if you keep on doing this, and you would always select the maximum, the action that maximizes your reward or return, you would always keep on selecting the right door. However, the question is, are you sure that you have chosen the best door? Because in the end, maybe there is a chance of 1 over 100 that actually on the left door there's a 0 reward, but in all the 99 other cases, the reward of the left door would have been 100. However, you will never see it, because you actually now keep on choosing the right door. So this is actually the problem. There is noise, stochasticity, and variance in the reward process, and this is in this case higher for the left door, and this is also something that you will see a lot in practice if you do reinforcement learning. So back to our topic. So making it a little bit more formal, the greedy policy improvement over Q, it doesn't actually use our model, our state probability transitions. However, it has other problems. And the problem is that you always execute the best action according to your estimated value function or state action value function. And the problem is that non-optimal initial choices may disorient your exploration in your environment if you're just exploiting your knowledge. And this also means that this leads to the problem that areas of the state space still remain unexplored for you. So you will actually never see parts of your environment. In the example before, you will never see what's behind the left door because you will never really explore what's behind it. Okay, there's also turns out to be a very simple solution which you have implemented in almost any reinforcement learning framework that you will get. It's just called epsilon greedy exploration, and the idea is very simplistic. So the idea just says that you either take the best action or you explore the action space. So that's the basic idea. And with epsilon, you define the probability to explore. And this seems very simplistic because actually it doesn't seem like to be informed of anything, but it's really hard actually to do much better in practice. However, you will see this in our exploration strategies lecture that we have at the back. So actually you define a small probability, and in the small probability you will not take the action that your argmax policy would suggest, but you take some other action that you might also have taken in the past, but just take another action and just define the probability something like 10%, which will actually guarantee that you keep on exploring the state space without relying only greedily on known information. And there is also a formal proof that any epsilon greedy policy pi prime is an improvement over the previous epsilon greedy policy pi. This is something that we really always need to be aware of if we do this generalized policy iteration scheme. If you're interested in a proof on this, in Dave Silver's lectures on reinforcement learning in lecture 5 on model-free control, slide 12, there is a small proof that actually tells you that this is really the case. Okay, what can we now do? Also provide, there's also what we always do is we want to formal proofs, and in practice we want to maybe also decay epsilon over time. So what you usually do is you can also put this in a more formal framework, which is called greedy in the limit with infinite exploration Monte Carlo control. So what you usually do in practice is you start with a very high probability of exploration, almost like 1, and you linearly or cubically reduce the exploration rate, but in the end you will be close to 0 with the exploration probability, but always having a small portion of time where you actually explore. You can also be more formal with that. You can also formulate this in a Monte Carlo fashion. So you keep up a visitation counter on your state and action values, like your Q table, and this means whenever you actually are in a state S and you selected action A, so actually if you gained an experience sample from this, you keep on incrementing a visitation counter, and depending on this visitation counter value, this is then turned into something like a learning rate. So actually whenever you keep updating your Q value, your learning rate is higher with lower visitation counters. So this is also something like a decaying learning rate for states that you have visited, where you have already seen many information before. This also converges to the optimal action value function if you use this annealing strategy for your epsilon. Okay, let's go back to where we actually started. So our idea was to do the greedy policy improvement over Q simply at this point, and we had the problem with exploration. So what we now do is in here, we just put in an epsilon greedy exploration in there. meaning that our policy improvement, or the policy that we actually generate and that we then use, is the epsilon greedy policy improvement over Q. Okay. So what you've now seen is the question is also what we've seen in policy iteration. The question is, when do we actually switch between all these steps? So in here, what you can actually do is, or what we did in the policy evaluation, as we have introduced it in the second lecture, we started with a random initialized value function and policy, and we actually knew that we actually estimated our Q function if it just have converged. So if if our updates are actually below some threshold value delta that we actually defined. And what you also have seen in the policy iteration example, you do not really need to wait until convergence to actually do the greedy policy improvement step. So what you can actually do is, maybe after each episode, you run an episode, you estimate your Q function, you update your Q function, and then do a policy improvement step. So which actually ends up in estimating something like an approximate of your Q function, also using Monte Carlo or something else, and then using this approximate of the Q function, update your policy. And if you like keep on doing this, what you really do in practice, you do not wait until the episode actually finished, because we have seen this like with TD learning, there's no real need to actually wait until an episode has finished. What we actually do, we want to update our Q function after each time step. So we want to immediately use the freshest experience sample that we get from the environment to update our value function, or Q function in this case, which is something we introduced in the TD learning example, where you have seen that doing this is much more effective in practice. So we apply the idea of TD learning to the Q function and to the control problem. If we do this, we end up in an algorithm that's very famous in this area, and it's called SARSA. SARSA is a so-called on-policy control algorithm. On-policy means that the policy that we actually use to update our Q function is actually also the policy that we use to select the actions that we take in the environment. So this is on policy, in contrast to off policy, which we'll see in a minute, where we actually update our Q function with respect to a different policy that we actually follow selecting actions in our environment. I will tell you a few more things about this in a minute. Why is the algorithm actually called SARSA? I also wondered it a lot in the past, but there's a very intuitive idea behind it, because the update step in here is actually called SARSA. So this is why we call this algorithm SARSA. So the update actually incorporates the state and action that we are in, the immediate reward that we get, the state S prime that we are ending up in, and the action A prime that we would select in that state. So SARSA is actually the application of time difference learning onto the state action value function Q. SARSA uses an epsilon greedy policy improvement and updates the Q value at each time step. So maybe let's take a minute and step through the pseudocode of this algorithm shortly. So this is in the beginning we do the initialization, which is very similar to what we did in TD learning, where we estimated the value function. We initialize our value function for all our states and actions arbitrarily, except that our terminal states have a 0 value in this point. In principle or in theory, you could like initialize it arbitrarily. However, the performance in terms of sample complexity, as already you saw in TD learning, really depends on how good your initialization is, because you're always, and in this case also, you bootstrap your state action values. Okay, if we have done this, we make like an infinite loop over episodes, and so we run in episodes, and what we do is we get an initial state from the environment that we are in. So if you usually start in an environment, you get an initial state. given for the environment. And what you now do is, in the beginning, you choose an action A to take in state S using your policy derived on Q, which is in this case maybe an epsilon greedy policy. So you actually select the action over an epsilon greedy policy, which in epsilon cases would be a random choice, and in the other, in 1 minus epsilon cases, would be the maximum Q value for a given state S. And then what you now do is, for each step until the episode runs or the episode finishes, what you do is you take the action that you selected and you observe your reward and your next state. And what you would then do is, you would, because actually you received the next state, you would now choose an A prime from S using your policy. So this is actually what you would now do is, you would select the action that you would take next. And next, you will actually use the experiences that you got in here to actually update your Q function. So this is the case, you need to first choose the action before you update the Q function, because then this would be different. And your update is like as similar as it can be. So as we also have seen it for the value function, for state value function, we can also do it like for the state action value function as well. So nothing else that our new value for QSA is nothing else that the old value of QSA plus some learning rate times the immediate reward that we got from the environment plus the discounted Q value of the next state and under the next action that we said that we will take in the next state. Because we actually have our behavior policy that's also used to use the target value that we're optimizing towards this, which is the action that we will take next. Because actually this is what we're taking next, and this is also the Q value that we're optimizing against, minus the old Q value to have something like an error target that we want to minimize. Okay, and then we just reinitialize S and A, and then we loop over again. We do this until the episode finishes, and if the episode finishes, we just start over with a new episode. And we can run this until the Q function is converged, and we're at the our optimal policy pi and optimal Q function Q star. Why are we applying time difference learning instead of Monte Carlo in here? It's actually the same advantages and disadvantages that we have seen in the last lecture. So the application of TD just results in a lower variance of the samples, which is particularly important because we're doing off-policy learning in a minute. We can learn online and we can learn from incomplete sequences, which is something that is very common in practice. Okay, so maybe let's see an example how this actually would look like. What you see here is like a windy grid world, which is something that you also find very often in practice. And you have a start state, and you have a goal state, and you want to go from start to the goal state as quickly as possible, because for each step that you actually take in your environment, you get a -1 reward for it. Let's just assume there is no discount in here. And what you see is also, if you are in this state and you're transiting to this state, you see that there's 1 in here, just meaning that if you're transiting in here, each time step you will get blow up 1 into this direction and actually 2 also in this direction. And the question is now, how can you come up with a policy that's optimal in this case? There's one thing, going from here over here and trying to reach the goal state is not possible, because the wind will blow you to the north brick inside here before you actually reached the goal G. It turns out that the optimal policy looks like this. This is the only way you can actually get in there. And it's just saying that go right, always go right. The wind will blow you to the north brick, and then you cannot like blown out of the state space. And then you go to the right, and then you can reach the target over here. And this is something that you can really easily implement with SARSA. If you're like really interested and curious, just implement the grid world and implement SARSA on it. You have seen it's like only a couple of lines in source code, and you will see that you will come up with this policy. What's always interesting to see is also the kind of visualization of the learning process in here. And this is a very like common and intuitive way of actually plotting the performance of learning and training in reinforcement learning, you will see the time steps, which is actually the same as environmental interactions. So this is the number of actions that you have taken in total, which is always something that we want to minimize in reinforcement learning, because we actually say that training is cheap, we can do this on the GPU, but usually the interaction with the environment is a real costly thing. That usually is either costs me real time, like time in real world, or it's like costly because I can damage something. And what you see here is basically what you see is that as the time steps progress, you will see that the number of episodes that you actually finish grows, and meaning that the gradient is actually growing. And what you see here, at some point you will have a gradient at this point, which is somewhere like here, and then the slope of the gradient will actually tell you the length of the episode. And if you have like a tangent in here, you will not get better than this, and you will always have this tangent. So the slope actually tells you the length of the path and how long or how many steps you actually take until you finish the episode. And the interesting idea is once you actually, in the beginning, what you see is like learning like progresses very slowly, and the reason behind this is actually that it takes a lot of time actually for your agent to reach the goal, because the episode is only terminated when you reach the goal state, which means that you have to explore a lot your environment to actually get to end the episode, to actually see something that in your bootstrapping you can ground your information to. And once you've seen the goal state, you actually keep on progressing much faster, and you will then go to the solution actually. Okay, to sum this up for SARSA a little bit, what's the pros and cons of SARSA and when to use it? What's the disadvantages and advantages? So SARSA is an on-policy control algorithm, meaning that the Q values we use at our target to minimize in our update function is the same policy that we actually use to select our actions that we take, meaning on policy. A real pro at this of SARSA is actually that we process each sample immediately. So we do not need to store them in a buffer or in a memory. We can like learn on the job, take a step and do it, and learn from it and go the next step. Also, the update cost per sample is like really minimal. So we have to do some like 2 or 3 additions and a multiplication, and basically that's it. So usually the interaction with the environment is much more costly than the update of your Q function. However, there's also a few disadvantages with SARSA in this case. So actually, as we have an on-policy sample collection, this poses constraints on the sample collection. We will see this in a minute, because actually you will always do the epsilon greedy step, and this is actually a little bit constraining on how we can actually use actions to update our Q function. In practice, compared to other algorithms, I mean, you didn't have seen so much algorithms for a comparison right now. It requires a huge number of samples. And this has also something to do with making minimal use of each sample. Because actually, we see examples, I think, in 2 lectures from now, where you actually reuse also samples that you have seen once another time. So the reuse of examples of experience samples is not that easy in practice, but you will see this. What do we have? We require a careful scheduling for the learning rate and also the epsilon greedy strategy. This is something you really need to tune, and there's also a hyperparameter search that you would actually need to run to actually get the best results from it. The ordering of the samples influence the outcome. We have seen this. So our experience samples are correlated because we see experiences in trajectories, and as they are correlated, of course, the ordering of the samples also influences the outcome. It exhibits instabilities under approximate representation. So actually, we will see in a few, we will see actually next lecture that it's not always really practical to keep maintaining a table of all your states and actions, because of several reasons. And if we want to approximate the Q function, it's very unstable. You will see this in, I think, next lecture. And of course, we need to it requires a careful handling of the policy greediness, which is actually what I said, that we really need to tune epsilon also to, at the one hand, find the optimal solution, and on the other hand, not taking too long and updating too much without actually exploiting the environment. There is also as we have seen in TD learning, there's also ways to include n-step returns. You can like come up with n-step SARSA and also lambda versions of SARSA, where you actually make a weighted sum of returns that you can get, which also allows you somehow to turn the idea behind SARSA, which uses TD learning, also a little bit into the Monte Carlo direction. I have a pseudocode, I think, in the next lecture, in the next video, where you can actually think about or think of a Monte Carlo version to do Q learning. And this is something I will tell you in the next lecture. So as it sees, SARSA is an on-policy control algorithm, and which means that we are very constrained on the samples that we actually get from the environment and that we can learn from. And a slight variation of this is actually something that you will see a lot in practice, which is called Q learning. Q learning and SARSA are from their derivation, from their idea, they're very similar. There's only one small difference which makes them in practice like really different. And the basic idea of Q learning is that Q learning is off policy. Off policy meaning that the policy that we use to select our actions is a different policy that we actually use to update our value function. And this sounds like not a big deal, but all our proofs that we have seen so far that talk about the convergence of general policy iteration always assume that the policy that we are evaluating is also the policy that we are updating, and this is like violated now. But however, it allows us to do a lot more things in the upcoming lecture. So like this is really a way to really believe me and actually to get this, that this is also working. So as you have seen, maybe we just go to the pseudocode and then maybe you get the intuition behind it. So it's really similar. The initialization step is the same, and then we also have a loop for each episode that we're doing. And what we do in the beginning, we get the initial state, and then we also loop for each state in the episode. And this is also the same. We choose an action A from our given state S that we're in using an epsilon greedy behavior policy pi. So now we have a behavior policy which actually defines how to behave. And what we now do is we actually take the action and observe the reward in the next state. And now instead of selecting the next action to actually also formulate our Q target, we say, no, we have seen the next state. So the best thing that we can actually do would to update our Q function towards the maximum Q value that the next state actually has, and not the epsilon greedy Q value that the next state actually has. So this is the difference in the update function. So our Q function actually is updated with a learning rate alpha again, and our target is actually the immediate reward plus the discounted maximum Q value of the successor state minus the current value. So in this case, what we had done in the beginning, in this case, we selected the Q value of the action that through an epsilon greedy policy we selected, which may not be the action that maximizes the Q value. It might be a lower one. And if I select a lower one, actually, through the epsilon greedy policy, my target is not quite the best I could get. So we actually have our state here, and this is the successor state, and there's a lot of actions that we can take. We might take this action due to our epsilon greedy behavior policy, but our target policy says, from the current knowledge I have, this is the maximum Q value. So, of course, agent, you can do this action, but my update, please, is in relation or in respect to this action, this Q value. which is like a normal thing to do. And however, this is off policy, meaning that our behavior policy is different, and this is also different with the Q functions and the state value functions, and violates somehow the convergence properties that we actually assumed. However, it now also allows us to reuse experience that we have from old policies. So what we can actually do is we can take arbitrary experience samples from the past and keep on iterating and improving our value function. And this is like a really nice thing to do, because in the end, this would reduce our sample complexity. And this is actually the main thing that we want to optimize. We want to minimize the environment interactions. And this is something that allows us Q-learning. Q-learning allows us to reuse experience samples and hence to keep on iterating on the experience we already have. To sum this up, of course, many of these arguments, many of the pros and cons of Q-learning also hold, of SARSA also hold for Q-learning, with some small differences in here. So also in Q-learning, the same thing as in SARSA, we process each sample immediately. So we just experience it, we use it, and we might throw it away. And we have a minimal update cost per sample as in SARSA 2, because the update function is almost the same. And we have also no constraint on the sample collection. So actually we can use an epsilon greedy policy and define this like we want. But this doesn't have an influence on our target update or minimization of our Q function. Still in, depending on your problem, of course, and depending on the methods and also in relation to the methods that we see in the future, it requires a huge number of samples. It also requires still a careful scheduling of the learning rate, like in any other machine learning algorithm. Per sample, you still make minimal use. However, in the next lecture, you will also see that how you can actually mimic that a little bit. Also in here, the ordering of sample influences the outcome, of course, because the correlation between the trajectories while learning on the job is still given. We also find a way to solve this in the next lecture. And also it exhibits instabilities under approximate representations, still like also for SARSA, but this is something that we also address in the next lecture. Okay, maybe one more example or one more slide to actually tell you like a little bit of the intuition of the difference between Q-learning and SARSA and how they are actually different if you run them on an example. So we have seen this cliff walking example also in the past, although in a different like visualization. What you see here is you see a start state and a goal state, and the job of the agent is actually to go to from the start state to the goal state while maximizing the return. And the return of the reward process is defined like this. The agent gets a -1 reward for every transition it takes in order to foster that the agent actually goes to the goal as quickly as possible. However, falling off the cliff gives him a -100 and ends the episode, actually taking him back to the start state. There is no discounting, and we assume that we use an epsilon greedy policy with a probability of exploration of 10%, and no learning rate decay for epsilon greedy for both SARSA and Q-learning. So now the question is, how are they performing over the course of the episodes and training? And what you've seen here is, for instance, the safe path and the optimal path. So the optimal path would of course be the path that minimizes the number of steps that we take and goes from the start to the end state immediately. And the safe path would be like going away from the cliff, because there might be a chance I would fall over, and go to the goal state. And the question is, because there is no noise in the environment, why is there a chance to actually fall over the cliff? And the thing is, we use epsilon greedy, which basically means that there is a chance of 10% of doing not the optimal action, which in this case would maybe mean to go down and fall over the cliff. Okay, so if we do this, and if we would run SARSA and Q-learning, SARSA would actually keep on choosing the safe route, because there is always the chance of falling down, and this is incorporated in the update of the Q function. So the epsilon greedy policy, which will always be taken, will result in always the case that we could fall off the cliff, meaning that this also has an influence on the Q values, meaning that it is better to actually go to the north brick and then go to the right, because this is the safe path. And even with an epsilon greedy exploration strategy, we would always get we will never fall off the cliff. However, Q-learning, although Q-learning follows an optimal, although Q-learning follows an optimal policy, the greedy policy or the optimal Q function that we actually estimate from the behavior policy is actually going over the optimal path. So although Q-learning at some times selects a non-optimal action that will let us fall off the cliff, this does not have an influence on the updating of our Q function. Our Q function will always update towards the maximum I have seen so far, and this is then in the end always being the really maximum value without actually doing something with the epsilon greedy policy. However, if we monitor both of the algorithm or the agents in practice, you will always see that the sum of the rewards that you see during an episode is lower with Q-learning, because Q-learning in the actual execution of the actions isn't really taking into account that I fall over. It just optimizes the optimal Q function, which is the optimal path, but the epsilon greedy policy would at some points, a 10% chance, select the non-optimal action and fall over the cliff, maybe. And this is why you will see a lower performance for Q-learning in here. If you would decay, for instance, epsilon greedy over the course of training, Q-learning and SARSA, so Q-learning will actually, you will see actually a very low rewards like -10 for Q-learning, because actually Q-learning will then behave greedily with respect to the policy and just go the direct route, having a -10. And if you would carefully decay epsilon greedy with SARSA 2, also SARSA will approach the optimal Q function and then from the top to the bottom slowly. But this requires a careful schedule to actually do this. Okay, so far for Q-learning and SARSA as two model-free on and off policy model-free control algorithms. One final remark on this. So both SARSA and Q-learning are like variants that use the idea of TD learning put on the Q function and making them not suitable for a prediction problem, but for a control problem. But there's also a Monte Carlo based way of doing control. And this is actually what I put you here. We did not get this into full much detail in here because it's actually not that relevant in practice. But you, however, will see some of these ideas or actually how this works if we do policy gradients, I think in 3 or 4 lectures ahead. But the general idea is actually to use Monte Carlo rollouts where you have different starting positions and you just generate episodes. And for each of the episode, you just do a Monte Carlo fashion update of your Q function, which actually also turns out that you will get the optimal Q function in the end. Okay, so there's some references. So the main references for this section is still Sutton and Bartos reinforcement learning and the initial work from Bellman with the dynamic programming. You have some further reading material that you can look into, but they are really similar to this lecture. And there's also still the blog from Andrei Karpathy with some programming examples that you can always use to play around, which you can also use for this.